Hello everyone, this is Claude Nicollier. I'm a professor at the Swiss Federal Institute of Technology in Lausanne, PFL, and I'm recording this short video from my office. I hope you have a good time at the MedTech. I'm sorry I could not join you today, but I've been asked by Marcel Egli to say a few words about the physiological adaptation to the zero-G condition and the recovery after return to Earth. Now, in a space flight, whether it's long duration or short duration, you have several phases. You have the ascent to space. You have then the exposure to the space environment, which means zero-G conditions or close to zero-G conditions, and of course, somewhat heightened particle and cosmic ray exposure. This is the on-orbit phase at the end of the mission, whether it's short or long. You have the orbit burn, whether it's with Soyuz or the space shuttle or any other space vehicle, and return to Earth, which doesn't take a long time, but typically of the order of 1 hour or less. Then you have the Earth conditions, where your body is exposed again to the 1G conditions, like everyone else on planet Earth. Then you have the short-term recovery on the 1G condition, and the longer-term recovery. And I will describe these various phases for short duration, for long duration flight. The short-term adaptation to zero-G conditions is the same whether you're on a short duration or long duration flight. You go through a period where you need to learn the strategy of moving in the spaceship from one place to the other. Very often you also suffer the space adaptation syndrome, typically nausea, sometimes vomiting, but this never lasts a very long time, typically a few hours, and after 1 or 2 days you are fully in good shape. You have also fluid shifts. The fluid moves from the lower part of the body to that part of the body. You have kind of swollen head and sometimes a little bit of discomfort like a headache, but you can take care of that with aspirin or other drugs. This stays with you during the whole mission, whether it's short-term or long-term. You always have that somewhat increased blood pressure in the upper part of the body. Now, what you have if you are on a long-duration spaceflight is, of course, bone mass loss. This is well known, and you have muscle deconditioning. This is taken care of to a large extent by physical exercise made systematically by astronaut and cosmonaut on the International Space Station, typically about 2 hours of pretty strenuous exercise per day. When I say day, I mean 24 hours in the flight plan. Of course, the whole activity plan is divided in these slices of 24 hours so that we can work quite efficiently, like here on Earth, based on this well-known and standard cycle of activity and rest. For short duration spaceflight, I would say that the muscle deconditioning and bone mass loss is negligible. That's what I experienced on the space shuttle, or anybody who flew on the space shuttle. We had planned a short period of exercise every day, typically half an hour, which we did normally, but not always, because again, it's like a bed rest. If you have bed rest in a hospital for 10 days and you get up and you're able to walk again, and you don't have a need for a long readaptation. Now, the problem of radiation is existing for short duration or long duration flight. It's very depending on altitude of the flight. I had 2 of my flights, shuttle flights, which were at 600 kilometers altitude, the altitude of the Hubble Space Telescope. That was for rendezvous with the telescope and repair work with spacewalks. And at 600 kilometers, you are exposed to quite a bit more radiation per day than you are at 400 kilometers, which is the altitude of ISS. Typically, we were grazing the bottom part of the inner radiation belt, especially when we were coming in the South Atlantic anomaly. And we had a visual effect of cosmic ray particles impacting the eye, as we had flashes in the eye. I never had any of this on my low duration space flights, which is the case for 2 of my flights at 300 kilometers altitude. And as far as I know, this is not experienced by astronauts on board the International Space Station. So beyond the problem that I mentioned, muscle deconditioning and bone mass loss, which again are not too severe because of countermeasures by exercise, The exposure to cosmic radiation is, of course, a problem of spaceflight. Not too severe for low Earth orbit, except if you go to these 600 kilometers altitude, as I mentioned. Typically, on a shuttle flight, you had an exposure of a few rems per flight, and I know for 6 month duration space flight, it goes to maybe between 5 and 10 rems of radiation, which is not too bad. Obviously, this problem will be much worse for human spaceflight beyond the low Earth orbit, going towards the moon already, or to Mars, or other destinations in the solar system. Now, at the end of the mission, of course, you have the orbit burn, return to Earth. You go through relatively high G condition during the return to Earth, and no big deal. Then when you come back on the surface of the Earth, after short duration flight like I experienced, what was striking was the hypersensitivity to gravity. I had the feeling that everything I was carrying was very heavy, whether it was a camera or the glass of champagne following the medical check post-landing of the space shuttle. These all looked very heavy, but this is a sensation you have for a few hours, maybe 1 or 2 days. After that, it disappears. Of course, after a long-duration space flight, the readaptation to the normal conditions on Earth takes much longer. I heard somebody say that typically the readaptation on Earth will be as long as the duration of the spaceflight itself, which means that the shuttle is going to be a week or two, which is about true, although after 1 or 2 days you feel pretty close to normal on Earth. And after a long duration spaceflight, it's going to be several months. Of course, having only flown short duration flight, I'm not totally oriented about the detailed recovery of the human body to the conditions on Earth following long duration space flights. But obviously, people get back more or less to normal. There's one thing that is still a concern, is the modification in the eyes, whether it's modification of the eye globe or the optical nerve, which has been somewhat depressed during space flight, especially long duration, and it looks like we have some visual effects that remain long term after a return from long duration space flight. This is still being studied, but that's one of the concerns. All in all, the body recovers quite well after several months, but we may have a need for glasses or some corrections of vision following a long duration space flight. This, again, is still an active subject of research, and I don't have all the results. So that's it. In summary, muscle deconditioning, bone mass loss, radiation, visual problems. We may have also an immune system problem, but this is also still being studied. Of course, we had the experiment, famous experiment of Augusto Cogoli on Space Lab 1, the proliferation of lymphocyte in weightlessness, which was depressed in the zero-G conditions. And I know this is still a very active subject of research, especially in view of a long-duration spaceflight in object in the solar system. That's about it for the physiology. Of course, there are psychological effects. I won't talk too much about that. No problem, of course, on short-duration spaceflight. Long-duration spaceflight, if you go to Mars and during 6 to 8 months, you see nothing through the window except the Earth, pale blue dot becoming smaller and smaller, and the red dot, Mars, becoming bigger and bigger until you get there. But the rest of the view is pretty uninteresting because it's completely black. Remember that on any flight, when you are exposed to the solar radiation, which was the case for most of the trip of the Apollo astronaut to the moon, which will be the case for nearly all the time, except short duration parking orbit before getting the kick to go to Mars, they are going to be always in the sun, which means the sky will be completely black. So unlike astronauts on ISS, which have a permanent view of the Earth day and night, which is quite fascinating. The view of the Earth is an enormously attractive feature of a flight on low Earth orbit, and also the sky during the orbital night. We won't have that for the long duration flight to Mars. It's going to be all black with the sun in the field of view, and the Earth becoming smaller and smaller, and the Mars becoming bigger and bigger. So from a psychological point of view, this, in addition to the fact that there will be the time lapse for the communication, you ask a question to the ground, it takes a few minutes to get to the Earth, and then you get the response a few minutes later. Or if you communicate with your family or close friends, it's going to be always affected by this time lapse, which from a psychological point of view is going to be pretty hard. Anyway, I don't want to insist on the psychological aspect. I think they can all be resolved, but low Earth orbit is not a big deal from a psychological point of view. You're glad to be back to your family and close friend when you come back, and be able to go and walk in the forest and drink a beer and eat a pizza, which contrasts with the sanitized environment of the International Space Station. But I don't think this is a big deal. But for long duration spaceflight in the solar system, that's going to be more of a problem. Anyway, I wish you a good time for the rest of the MedTech conference, and I hope to see some of you someday, and I look forward to see the result of your discussions, and I wish you a good time, and have a nice weekend also. Take care. Bye-bye.